For centuries, these, the hills and valleys of New England, have bred and raised pioneers in ideas, in inventions, in developments. And today, another phase of pioneering raises a new and strange form against these ageless hills, a form that signifies pioneering with power, the power of the atom. The beginning, August 30th, 1954, when the administration signed into law the Atomic Energy Act to permit ownership of atomic facilities by private companies. On the next day, August 31st, 1954, representatives from major New England utilities met to form an atomic power company. Why? There were several reasons, all of them sound. Here are some.
Because it was expected of us, electric utilities have an obligation to provide the most efficient and economical service. That meant atomic energy. It was our job to try it.
Because we felt this was a job for private industry, not the government. Call this the old Yankee spirit, if you will.
Because the only way to learn the potentials of the atomic power field is to try it.
Yes, those were some of the reasons. There were others. A full-scale plant in operation would put us in the best position to benefit from new breakthroughs in the atomic field. Such a plant would focus attention on New England, attract allied industries in the atomic area. Finally, it seemed that the possible benefits outweighed the pitfalls. To learn answers costs money, but the answers in this case seemed well worth the risks. Such was the plan for a new element in the power network of New England, financed by private capital, aided by a research grant of $5 million from the Atomic Energy Commission. Total cost, about $50 million. Forming a company, however, was just a license to get involved in countless decisions. Where, for example, might such a plant best be located? A number of factors had to be considered. First, it would be handy to have it reasonably close to existing transmission lines. Second, an adequate supply of water was essential. Third, well, here a compromise was needed. Rail transportation would be most useful, even if it meant reconstructing some miles of track. Last, but by no means least, it would make things immeasurably easier if the people wanted the installation in their town. All the requirements, especially the last, were met in a site in northwestern Massachusetts on the Deerfield River. Water, power transmission lines, a railroad, and folks that were interested in the plan all added up to a final choice. The name of the town, ROWE, Massachusetts, site for pioneering with power. Decision 2. Which particular type of reactor would best serve the purpose? A number of other operating reactors was studied all the way back to the first nuclear submarine, Nautilus. Consultation with the builders of the Nautilus reactor, who had also been involved with many other atomic energy projects, resulted in the choice of a pressurized water reactor using slightly enriched uranium fuel and cooled by ordinary water. To understand it, to appreciate the functioning of this 136,000 kilowatt plant, let's look inside for a moment and see how a nuclear power plant works. Basically, the pressurized water reactor station operates on a simple principle, embodying a primary and secondary heat transfer system. In the primary loop, ordinary water of high purity, kept under a pressure of 2,000 pounds per square inch to prevent boiling, is pumped through the reactor. The reactor contains uranium fuel, which is the source of heat, and control rods to regulate the power level. The control rods absorb neutrons in the fuel area and make them available to cause fission. By further inserting the rods, the number of neutrons is reduced and power level declines. The water, after being heated by the fuel in the reactor, flows through a steam generator. There, it gives up some of its heat and is then recirculated by the pump, repeating the cycle. The secondary loop operates at a lower pressure to allow water to boil. Saturated steam is produced in the steam generator and flows through a turbine generator to produce electric power. The steam then goes to the condenser and, as water, is pumped back to complete and repeat the cycle. The use of separate systems prevents the possibility of transferring radioactivity from the primary system to the turbine and condenser. In order to condense steam to water in the condenser, to improve the efficiency of the plant, heat must be extracted. For this purpose, water pumped from the Deerfield River flows through pipes to pick up heat from steam being condensed and is then returned to the river. Notice that river water does not flow directly through the reactor or the steam system. Since reliability is a vital quality in power generation, the pressurized water reactor seems likely to be the workhorse of the nuclear power industry for some years to come. It holds the potential of becoming the first to approach competitive cost levels in the generation of electric power. The possibility of replacing millions of tons of coal at the end of expensive miles of transportation is, of course, an alluring one. Similarly, the idea that a few hundred pounds of uranium fuel could replace countless gallons of fuel oil holds out the promise of more economical operation. These, however, are long-range potentials. For the moment, the people who undertook to build the Yankee atomic plant know full well that the cost per kilowatt hour for the electricity generated there will be higher than that generated by time-refined conventional methods. But with the demand for power expanding at the rate of 6% a year, promising to triple in a couple of decades, and with the New England area the dynamic pioneer in most of the advanced concepts in atomic energy, the need to know the answers to electric power generated by nuclear energy is one which cannot be and will not be ignored. The next major step was seeking engineering help to integrate them into a practical unit. Boston's Federal Street held the answer to the type of engineering needed. For here was an organization which had been deeply involved with the design of other nuclear operations. Within its Nuclear Projects Division was gathered a group of people familiar with and anxious to participate in the job of bringing nuclear energy for power generation to New England. The date, July 1st, 1956, when a conference like this initiated the plant engineering and design. To take an idea from its roughest form through all the many steps demanded close teamwork between the engineer and designer, coupled with experience of the highest order. It demands also the use of all the mechanical and electronic assistance available in a modern and well-integrated engineering effort. From this team effort, from the day-by-day, week-by-week, and month-by-month detailed development, data study and analysis, a form and an idea took final shape. Mountains of detail having to do with all phases of the job, from cubic yards of earth to be moved to final installation of the reactor itself, had to be established, checked, and rechecked, until finally, three-dimensional and solid, the idea grew to a complete model. It consisted of these basic elements: the spherical steel vapor container housing the nuclear reactor itself, the turbine building where the heat from the reactor would drive the generator, the office building for administration of the project, and several other structures we shall touch on later in more detail. Yes, at this point, an idea had been made tangible, measurable, an idea for pioneering with power from the atom in the best New England tradition. Only one thing remained: build it. The date, September 4th, 1956. The operation, preliminary land clearing and radiation monitoring. But in other language, seen against the ageless hills, the beginning of another story suitably fitted to the long traditions of which these hills have been a part. After that initial date, significant moments strung themselves together like beads on a chain, thanks to planning and execution of the plans according to a carefully developed schedule. March 17th, 1958. Hungry tools biting out huge mouthfuls of earth, changing the face of the land. April 11th, 1958, the first of more than 2,500 tons of concrete to support the 125-foot diameter steel sphere, the 175-ton pressure vessel and its auxiliary equipment. Upon this concrete would rest the 8 reinforced concrete columns and the 16 steel pipe supports for the steel sphere. June 20th, 1958. Arms of steel for the turbine hall, where the turbines driven by the heat generated in the sphere would eventually produce 136,000 kilowatts of power to feed into the power network of New England. It is a mighty story and an exciting story. These scenes of continuing activity, of bringing order and form and pattern out of the raw and stubborn earth, out of inert steel and fluid concrete. This story of bringing out of the reams of paper, the models, the plans and specifications, something massive and solid, something too with a significance in its very conception that probes long fingers into the future. For it is truly the job of the pioneer to seek, test, yes, even gamble, to discover the answers that must be known before information can become progress, and progress can provide measurable benefits to mankind. Another major date, September 26th, 1958, when the last steps are taken to prepare for pouring of the initial concrete for the reactor structure itself. Sinews of steel, most of it 2 inches in diameter, for the tons of concrete which will be placed in one continuous pour so that the base of the reactor structure shall be without seam or joint. For 10, 20, 30 hours and more, the 3 derricks swing a continuous bucket brigade to the scene. Better than 2,000 tons of concrete webbed and sinewed by more than 100 tons of steel. 1,000 cubic yards of continuous pour, a feat to test machines and men alike. But a feat that is accomplished as planned, and the huge saucer-like base of the internal reactor structure takes its final shape, supplies the strength and protection needed for what is to follow. Other areas of the unique complex of buildings take their final shapes as well, and as the weeks go by, the complete plan begins to emerge. With a gross weight of some 1,400 tons and a diameter of 125 feet, the outer skin, the final protection for the reactor and its associated equipment, goes on. Many of the individual plates are machine welded on the ground into subassemblies. Each weld is X-rayed. And when the plates find their final place, the total length of welds alone runs to 1.5 miles, about 50% hand and 50% machine welded. And perhaps here, as the final steps are taken on the reactor sphere and the rest of the installation becomes each day more and more completed, would be a good time to stop for a moment and see just how the plant operates. As we saw previously in more detail, the splitting of the uranium atoms under calculated control produces intense heat. Enough, actually, in this plant to compare to the output of a steam boiler plant 15 stories tall. The heat from the fissioning material heats water that flows through the reactor core. The water is held under 2,000 pounds pressure to prevent steaming. This heated and pressurized water then is pumped through the steam generator, where it heats the water in the secondary system, transforming it into steam. This steam, as in any conventional steam generating plant, turns the turbines which produce the electric power. Yes, this is how pioneering with atomic power looks from the outside, and from here on, it is what happens inside that counts. Of primary importance is the neutron shield tank. Into it, the reactor itself will be set. The top section is a very heavy steel plate to support the weight of the reactor vessel itself. A 5-foot concrete wall surrounds the water-filled tank. The reactor consists of a heavy steel tank, shown here arriving by rail. This 30-foot-long tank has an inside diameter of 9 feet. Into this vessel will go the fuel assemblies containing 26 tons of uranium. Since the vessel will operate at a pressure of 2,000 pounds per square inch, it was built with walls 8 inches thick. The reactor, weighing 175 tons, was hoisted into the sphere by means of a powerful crane, which also placed the steam generators and other heavy equipment. With the neutron shield tank installed, the actual reactor vessel is now lowered into place. So, after years of effort, planning, decisions, and construction, the reactor itself becomes a part of the system. Next is one of the 4 steam generators which utilize the pressurized water heated by atomic fission to make steam to run the generators themselves. Arriving from the supplier by flat car, the transfer of it from car to its final resting place is a matter of high skill and experience. A different approach is the installation of such equipment through the opening in the sphere. Heretofore, such installations have been below or at ground level, but here, the 4 generators may be lifted directly from the railroad into position. For an idea of how they are placed, let's refer to another mock-up of the interior of the sphere. These generators are tied to the main reactor by the pipes carrying pressurized water for heat and tied to the turbine to deliver the necessary steam. To control, guide, and direct the operation of the reactor, to safeguard the installation, to provide the required heat for the given load, a system of interlocking controls is installed here in the plant control room. From this main panel, trained operators are able to run the atomic furnace and to supervise the performance of the entire power production flow. 2, they can and will note data over the course of the test operations to come later. From such data, and from the practical experience gained, will come some of the answers sought in this bold venture. In the meanwhile, a little overshadowed by the exciting implications of nuclear energy, the installation of the electric generator itself goes on. As previously mentioned, the generator is driven by a steam turbine. Here, the cover is lowered into its position over the blades, which will capture the energy from the steam. When the generator is operating, the whole venture will make sense. For the cost of providing each of the kilowatt hours generated here will be watched and studied by all the participating companies that make up Yankee Atomic Electric Company. We have talked a lot about water throughout our story. In fact, it was one of the primary influences in the selecting of a site for the plant. To supply all that is necessary for the day-to-day functioning of the plant, an unfailing supply is assured through the installation of the intake line into the pond. And so, a plant that was only an idea a few short years ago now stands commandingly against the ancient hills of New England. In the meanwhile, miles away, the uranium, the actual fuel for the reactor, has been made ready. From the arrival of powdered uranium oxide and sampling of it for production, fuel fabrication is a job that requires care and skill. Mixing the oxide with the plastic binder puts it in shape for further processing. Pellets, made from the mix by pressing and sintering, arrive in corrugated shipping rolls. From each shipment, pellets are selected at random for inspection. Visual inspection for chips, cracks, and so on begins a long series of quality controls upon which the ultimate reliability of the reactor core will depend. For storage, preliminary to the loading of the actual fuel tubes, the pellets are loaded into transfer tubes. At the same time, the stainless steel fuel tubes are checked in an eddy machine to be sure the walls of the tubes are perfect. Actual loading of the fuel tubes is a highly specialized job. Each tube, when completed, contains 150 pellets of uranium oxide. The pellets are positioned and locked in place in the tube by means of a series of crimping and positioning operations. The full tube, as it is retracted from the positioning rod, measures 8 feet in length. There are a number of other steps leading to the first subassembly, where the fuel rods are stacked in a stainless steel fixture in preparation for the furnace brazing operation. After brazing and cleaning, we have completed subassemblies, 9 of which are stacked to form a bundle or fuel element assembly. And thus, a fuel element assembly is born. A 900-pound, 300-rod assembly joined together under precise tolerances. Atomic fuel, a dream of yesterday, now in practical, usable form. The Yankee crew that has spent months in intensive training and study now fuels the reactor with its precious uranium. 76 of these assemblies containing the 26 tons of uranium make up the core itself. Now the day arrives toward which all the massive effort has been directed. The day when, in the language of the nuclear people, the plant will go critical. This is the moment when the rods will be moved to initiate the first test of the reactor, when it goes critical for the very first time, when the silent power of atomic fission will write another chapter of New England progress. The date, Friday the 19th of August, 1960. The time, 19 minutes after 8 p.m. The control is moved, and generation of power by atomic energy takes another long step forward toward reality. The reactor goes critical. That one small motion at the control panel sets a complete cycle into the first phase of its operation. And later, on November 10th, 1960, an announcement was made of significant importance to the entire future of electric power in the Northeast. The nation's newest atomic power plant was now operating and at a cost well below that originally estimated. During the balance of the year, electric output is stepped up slowly toward the output capacity of 136,000 kilowatts. Such is the beginning of a story, the ending of which cannot yet be even guessed at. A story that holds the promise of a way to equalize New England power costs with those of the rest of the country, and the promise of a great deal more of lasting value to everyone living in this storied section of the country. Around this new process, a number of brand new industries will emerge and grow to major size. Here are just a few ideas as to these new undertakings. Fuel fabrication, the making of cores that may finally replace coal and oil. Some New England firms have already started on this kind of thing. Controls and instrumentation for the reactors. Where better to make them than in the region and by the people where craftsmanship has for centuries been a byword. Reprocessing of spent fuel. Facilities that are part of the ROWE plant take care of storage of the spent fuel. But in the reaction process, many byproducts are formed, some of them of great value when refined and reprocessed for other uses. How many such byproducts and new products? Here indeed is a broad area for further development on the part of many new enterprises. Finally, a tremendous opportunity for basic research and development in a region which has, since the very beginning, initiated such projects in its independent laboratories and universities. Yes, here in this modern-looking plant in the hills where pioneering has long been a way of life, is the promise of much more than just another way of producing electric power. Here is something that heralds a new age of industrial growth, of development, of research. A growth that has its initial impetus in the will and determination of New England people to accept the never-ending challenge of pioneering with power.